Hello, thank you for visiting my channel. This video is based on a problem I showed on my Facebook page. I explained to my followers that I would post the solution on YouTube. This problem deals with two segments of a side of a trapezoid, which are known. The top and bottom, the bases of the trapezoid, are not known, but there are three equal segments. Two of them are collinear on the slant height of the trapezoid. When I initially saw this problem, or one like it, I thought, is there enough information to solve? So I worked through the problem and discovered that yes, this can be solved. There is enough information to solve it. So I will follow through the solution at this time. The first thing we want to do, and this is not necessary, but I did want to show that the midline of the trapezoid passes through the midpoint of segment BE. And we see three segments all connected at the same vertex. So I'm suspicious that that would be in a circle. And so point C would be the center of a circle. AD equals AV plus VD. So we have this whole segment on the left. It's going to be this bottom piece, which is 6, and this top piece, which is 8. They're going to add together to give me 14. And I just showed the midpoint of 7. It'll have a little bit of importance in this proof, but not much. It is important, however, to understand that the midline, MC, bisects AD, but it also bisects BE. BC, CE, and CV are all congruent. That's these three, and I labeled them with X just to make it easier to follow. Now that we've done that, I want to look at these three segments. Because I suspect there's a circle involved, BE will end up being a diameter, and CV will be a radius that radiates from the center. So we could draw our semicircle, and we all know that a right triangle is inscribed in a semicircle. Construct circle C such that BE is the diameter, point C is the center, and point V is on the circumference. So this is what I did. I took point B and point E. They're the diameter of my circle. C is the center. And I knew that point V, if I gave it that same radius, X, I knew that would be a right angle by the postulate. So now that I know this, I also know that this segment will intersect at point C. So now we have two triangles that are inside the trapezoid, but that also gives us two other triangles that share the hypotenuse with the two triangles inside the circle. So now we're going to use triangle postulates to prove the angle relationships. Now, when you look at the two triangles, the one on the top, AVB, and the one on the bottom, DVE, those two triangles, the angles are connected around point V. Now, if you look at the three X's, the diameter of the circle, which was BE, and the segment that comes off of it, which is CV, it's at a right angle, and that was shown in the diagram. That means that these are right isosceles triangles. Both the bottom and the top are both right triangles, isosceles triangles. So we know that BVE is a right angle, so the angle above and the angle below will be complements. Angle AVB and DVE will be complementary. If we look at the individual triangles, the triangle at the top, AVB, it's a right triangle, and it has the same angle as DEV. This is pretty much the same triangle, just transposed when you look at it. So now that we can see the relationships of the complementary angles, we can further use triangle similarity postulates. In this case, it would be triangle congruence postulates. We're going to use the similarity postulates and the Pythagorean theorem to prove the triangle side lengths. BV, that is this green diagonal on the top piece of the trapezoid. It's going to be the sum of BC squared and CV squared. And we call BC and CV both x. So now we have BV squared equals 2x squared. We take the square root and we get BV is x square roots of 2. We do the same process for segment EV. Segment EV is this green diagonal down here at the bottom. It follows the same pattern because both the legs are x. So EV is also x square roots of 2, which is convenient as far as solving. I go to the proportion part. So corresponding parts of similar triangles and congruent triangles are proportional, but in congruent triangles, they're congruent. So dV over VE. dV over VE is simply the sine function, and that would be the sine of DEV. And we know that we come up to the top, and we can see that AB over BV is also the sine function of the same angle. So we can say we can solve for AB by cross multiplying. Well, in this case, we don't even have to cross multiply. We substituted the parts and the x squareds of 2 on both sides canceled out. So AB was simply 6. We discover when we do the same process for DE and VE, we see that that triangle equals AV over BV, and we substitute the parts. And so we can find DE because DE over x squareds of 2 equals 8 over x squareds of 2. DE over x squareds of 2 equals 8 over x squareds of 2. And so we solve for that, and it comes out that DE is 8. So the top is 6, AB is 6, the bottom DE is 8. So we found the pieces that we need to find the area of the trapezoid. So that's a simple process. Area of a trapezoid is 1/2 the sum of the bases times the height. So 1/2, the bases are 6 and 8, and the height is 14. 6 plus 8 is 14. 14 times 14 is 196. And 1/2 of 196 is 98. So the area is 98. This is the solution to the original problem. Find the area of the trapezoid in the diagram below. Thank you for watching. Please like and subscribe.